Hey everybody, it's Mrs. Cat, and I am going to go over the answers to the review whiteboard. So I'm just going to walk through my process of doing all of these, which is going to be a Lewis structure, determining geometry, and then determining polarity. So with any Lewis structure, we want to start by finding the total number of valence electrons. So I've got 4 coming from carbon. I've got 4 chlorines at 7 apiece, which is going to give me a total of 32 valence electrons. Okay, carbon is in the center because there's only one of them. It also has the lowest electronegativity, so I'm going to go ahead and place that carbon in the center, put my bonds around. 4 bonds at 2 electrons apiece, that is 8 electrons used so far. So I'm going to start placing my remaining electrons in as lone pairs around the chlorines. All right, so 30, 32. I've used all my electrons. Now I want to check to see if I've fulfilled a full valence for all of my atoms. And in this case, I have. There's 8 electrons around all of my atoms. Okay, so there's my Lewis structure. Check. Okay, I want to determine my molecular geometry by looking at my central atom. So what we're going to see here is that I've got 4 bonding regions and 0 lone pairs around my center carbon, which means I have 4 electron regions, right? You check out your VSEPR chart, or your geometry chart, we're going to see that this geometry is going to be tetrahedral. Okay, now that we've figured that out, we've got to figure out whether our molecule itself is polar or nonpolar. So remember, what we're looking for with polarity is your structure, your geometry, and if you've got an equal distribution of electrons in 3 dimensions, right? So we want to think about what's happening with all these electrons, right? Do we have polar bonds in our molecule? Yes, right? We're going to see that these chlorine carbon bonds are going to be polar with a slight negative on the chlorine, slight positive on the carbon. The fact that they are equally distributed around the carbon means that this whole molecule overall is going to be nonpolar. Right? We've got an equal distribution of electrons, okay, which is going to make it nonpolar. All right, first one done. Okay. Second one, NOF, and I gave you the information that nitrogen is our central atom. So we've got 5 valence electrons coming from that nitrogen, 6 from the oxygen, and 7 from the fluorine, which gives me 18 valence electrons altogether. Okay, I know nitrogen's in the center. Doesn't really matter what side I put oxygen and fluorine on, but there's 4 electrons used so far in those 2 bonds. Okay. I'm going to start placing my remaining electrons around my my terminal atoms as lone pairs, and then we'll see what we get. So there's 4, 6, 8, 10, 12, 14, 16, 18. Okay. There wasn't any place else to put that last pair, so I had to put them on the center atom. We need to check to see if full valence has been fulfilled for all of our atoms. So if I look at fluorine, check it out. It's got 3 lone pairs and a bond. That's 8 electrons. It's pretty good. Okay. If I look at the oxygen on the other end, it also has 3 lone pairs and 1 bond, giving it 8 electrons, full valence. All set. Now nitrogen. Okay. 2 bonds and 1 lone pair is only 6 electrons. So what we're going to need to do is rearrange our electrons so that we have a double bond. We're going to do this on the oxygen and not on the fluorine. Right? Remember, this fluorine has 7 valence electrons already on its own, which means if it's sharing 1 electron with the nitrogen to form this bond, that's how it's going to get its full valence shell. Okay, so we're going to leave that alone at 1 bond. All right, now that's all set. So let's take a closer look at this nitrogen so we can determine our geometry. Okay, so this nitrogen is going to have 2 bonding regions Okay, one single, one double bond. It also has one lone pair of electrons for a total of 3 electron regions. Okay, 3 electron regions, one of which is a lone pair, is going to give us a geometry that is bent. Okay. Lastly, let's look at our polarity. Okay, so we want to consider the fact that we definitely have a lone pair of electrons on the center atom. Okay, but we also need to check for polarity of bonds. So 3.0 is the electronegativity of nitrogen, 3.5, 4.0. Okay, so we're going to wind up with slight negatives on our outside atoms, slight positive on that nitrogen. Okay, because those are different electronegativities on either end, on the fluorine and the oxygen, and there's a lone pair of electrons on the nitrogen, this molecule is going to be polar. Okay, and that's going to be uneven electron distribution. Okay, I'm going to abbreviate that. Okay, moving right along. COCl2. Check out our valence electrons. Okay, 4 from carbon, 6 from oxygen, 2 chlorines at, yikes, 7 apiece. Okay, that's going to give me 14 plus 6 is 20, plus 4 more is 24 valence electrons. Okay, carbon in the center, as we normally will see. Oxygen, chlorine, chlorine. Okay, that's 6 electrons used so far. Let's start placing lone pairs. 2, 4, 6. Okay, whoops, I didn't start counting. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24. That doesn't seem right, does it? Let me double check here. 8, 10, 12, 14. That's wrong. There we go. That was 22. Okay, there's 24. All right, we're going to check for full valence. Each of the chlorine looks exactly the same. All right, it's got its 7 valence electrons plus 1 shared from the bond. That gives it a full valence at 8. Okay, great. Both of those chlorines are the same. Let's check out oxygen. It's got 8. Yeah. Now, carbon, on the other hand, only has 6. So we're going to need to rearrange. Okay. We're going to, again, take one of the lone pairs from the oxygen and make it a double bond between carbon and oxygen. Again, this has to do with the number of valence electrons each of those has. Right? So there's our completed Lewis structure. Let's look at geometry. Okay. Carbon is our central atom. 3 bonding regions. 0 lone pairs on the carbon. Okay, yes, there's lots of other lone pairs, but we only care about the carbon. Okay, this is going to be 3 electron regions, which is going to make this trigonal planar. Okay, those 3 atoms attached to the carbon are all going to spread out from each other as far as they possibly can to make that trigonal planar geometry. Okay, checking out polarity. Okay, do we have an even or uneven distribution of electrons? Well, just by looking at this, we can see we have different atoms attached to the carbon. Those chlorines versus the one oxygen have more lone pairs on them. So we can already see that that's an uneven distribution of electrons, but we also can determine that those are going to be polar bonds between the carbon and the chlorine and the carbon and the oxygen. Okay, 2.5, 3.5, 3.0. Okay, so we're going to see that as well. So this is going to be polar, and again, uneven electron distribution. Okay, let's see here. What are we on? Number 4? CH2 or C2H2. This is acetylene, though you really don't need to know what the name of this is. We've got 2 carbons at 4 electrons apiece. Okay, we've got 2 hydrogens at 1 electron apiece, which means I've got a total of 10 valence electrons to use. Okay, carbons have to go in the center. Hydrogens have to go on the outside. Okay. Now, that's a total of 6 electrons so far. Before I try to place any lone pairs, let's look at what's happening. Okay, both the hydrogens have one bond. That's going to fulfill their valence shell. Since hydrogen only uses the first energy level, it has full valence at 2 electrons. Okay, now the carbons, again, are identical. They each have 2 bonds, which means they only have 4 electrons. Okay, what we're going to need to do here is to go ahead and place those extra 4 electrons that we need as multiple bonds. We're going to get a triple bond here. Okay, we're going to get a triple bond between the carbons. Okay, that's going to use all 10 of our electrons. Every electron is used, valence shells are filled, we're all good. Now, we have 2 center atoms this time, both of the carbons. Lucky for us, they are identical. So we're going to be able to classify the geometry around each of those as the same thing. So each of these has 2 bonding regions. Remember, be careful, multiple bonds still only count as 1 bonding region. Okay, we've got 0 lone pairs, which means we have 3 electron regions. Okay, 2 bonding regions or electron regions. Why did I say 3? It's definitely 2. 2 plus 0 is 2. 2 electron regions. That's going to make this geometry linear. Okay, now checking for electron distribution. This is completely symmetrical. We've got 2 hydrogens on either end, 2 carbons on the inside. This is going to be nonpolar. Okay, this is even electron distribution. And we're going to say this is symmetrical. Okay, fantastic. All right, moving on to one that's a little bit more complex. We've got CH3 in CH. Whoa, this is wrong. I'm going to change this. I'll change it in the slides before I publish it. But this should be CH3 CH2. Let's see how I can fix this here. Yeah. Let's cover this up here. CH3 CH2 NH3. I think I just copied and pasted it there and it shouldn't have been that. So let's rewrite this. CH3 CH2 NH2. There we go. That's a little better. Okay. So now let's figure out total number of valence electrons. I'm going to combine these all up. So I've got a total of 2 carbons. They each have 4 valence electrons. I got a lot of hydrogens going on. I've got, let me see here, 5 hydrogens, 5, 6, 7 hydrogens, each with 1 valence electron apiece. And then I've got that 1 nitrogen with 5 valence electrons. So that's going to be 20 electrons altogether. Okay. I'm kind of running out of space here, so I'm going to add a new page for me to use to do this. So I'm going to use that structures, the formula's structure and how it's written to help me out. So CH3 tells me I'm probably going to have a carbon with 3 hydrogens attached to it, followed by a carbon with 2 hydrogens attached to it, followed by nitrogen with 2 hydrogens attached to it. Okay, so now we can count up all of our bonds that we have so far. So I'm going to highlight them here as I count them. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, we've got 2 more electrons that we have left to use. And if we look carefully, we can see that they're going to have to go as a lone pair on the nitrogen. Everything else is a full valence, so we're going to have to place that extra pair there. Okay, now that that Lewis structure is finally done, we have 3 central atoms to assign geometries to. So 1, 2, 3. Okay, we're going to need to look at each one of these. Okay, carbon here has 4 bonding regions and 0 lone pairs. Okay, that gives me 4 electron regions. Okay, checking your chart, that's going to be tetrahedral for my geometry. Okay, this carbon here as well has 4 bonding regions. It has 0 lone pairs, which is going to give me 4 electron regions, which is also going to be tetrahedral. And then finally, our nitrogen, 3 bonding regions, plus 1 lone pair, also is 4 electron regions, but this time the geometry is going to be trigonal pyramid. Okay, I hope that when you see this structure, you can tell automatically that we've got uneven electron distribution, right? This is going to be polar. Uneven electron distribution. Okay, we can see here, right? At this end, we've got that lone pair of electrons on the nitrogen. We also can see that if we look at electronegativities, okay, we're going to get a polar bond between both the carbon and the nitrogen and the carbon, or excuse me, the nitrogen and the hydrogens, right? So we've got that going on. We've got an asymmetrical structure and we've got polar bonds that are not symmetrical. Okay, last but not least, we're going to look at a polyatomic ion. This is the nitrite ion, NO2. We've got 5 valence electrons coming from nitrogen, 2 oxygens at 6 apiece, plus that -1 charge means I'm adding in an additional electron. So we're going to get 18 altogether. Okay, there's only 1 nitrogen. The oxygens are going to go on the outside. We're going to place electrons as lone pairs until we run out. Okay, then we'll check valence. So I've used 4 electrons so far. 6, 8, 10, 12, 14, 16. That last pair goes on the nitrogen then. Okay, either oxygen on the end, we're going to check they both are identical with 1 bond and 3 lone pairs. That's 8 electrons, so the oxygen has a nice full valence. When we look at nitrogen though, we've got 2 bonds and 1 lone pair, which means it's only got 6. We're going to need to make a double bond somewhere in order to get that octet or the valence filled. So because the oxygens are identical, it doesn't matter which oxygen you move the electrons from. You are just going to wind up having 1 oxygen with a double bond and 2 lone pairs, and your second oxygen will have a single bond and 3 lone pairs. Okay. Remember, to show that we have added in an electron, we want to put our whole Lewis structure in brackets and then put that charge on the outside. Okay. We can go ahead and assign geometry here by looking at this. Okay. Center atom, which is our nitrogen. We've got 2 bonding regions. There's 1 lone pair for a total of 3 electron regions, which is going to give me a bent geometry. Okay, the last thing we want to do here is to add formal charge. So we want to figure out where did the extra electron wind up in our structure. So that's where our number of valence electrons is going to be helpful. Right? So I'm going to change colors here. Let's go blue. Okay, so remember, nitrogen has 5 valence electrons, oxygen has 6. We want to take a look at what's happening in the structure to figure out, okay, where are the electrons being shared? Where have they been placed? Which one's got the extra? So I'm going to go right to left. Let me take this highlight off here. We'll look at one of these at a time. Okay, this oxygen here. Okay, if it has 6 valence electrons to begin with, that means it's going to need 2 electrons to be shared with it in order to get a valence shell full at 8. Okay, that's what's happening here. Okay, 6 valence, right? Plus the 2 that are shared from the nitrogen-oxygen bond, that's going to give it its 6 plus the 2 shared, right? So that one, we don't see any extras going on there, okay? We look at nitrogen, 5 valence, which means it needs 3 more shared with it to get to 8. We're going to see those shared electrons as the bonds. So we're going to count these as, let me see if I can mark these out, right? There's 1, 2, 3, 4, 5. That makes a little more sense to color it, doesn't it? Okay, there's its 5 valence electrons. That's how many it should have assigned to it, plus the 3 shared. That one's all set, which means we should have our oxygen on the left here is the one that has the extra, right? So if we count these valence electrons as 1 from the bond, right, plus the one that's shared, there's 1, 2, 3, 4, 5, 6, 7 that is one more than the oxygen actually has for its valence electrons. So we're going to show this as a formal charge by showing that the extra electron, let's move these off, was added on this oxygen by putting that formal charge onto that O there. Okay, so that's really everything that we need to do for 7.2, which is looking at the structure and the geometry of molecules. So can you draw a Lewis structure? Making sure that you use all the valence electrons and you fulfilled valence for all of your atoms. Okay, can you assign geometry to central atoms using Vesper theory and your geometry chart? Okay, can you determine if a molecule is polar or nonpolar based on the electron distribution? In order to do that, you have to look at number of lone pairs on center atom and polarity of bonds. Okay, and then the last thing we did here was Lewis structure for polyatomic ion, checking to see where the electrons were gained or lost in the formal charge. Okay, so I'll post the full key of this as a file as well. But if you have any questions, make sure you either reach out to me or to your own chemistry teacher. And I hope you have a great rest of your day.